Okay, next we start to take a look at rotational energy. We'll deal first of all with rotations about a fixed axis. That is an axis that is fixed with respect to an inertial reference frame. So here's a brief run through or a brief description of all of the quantities associated with work and energy that we've already seen in the context of translation, for example, back in chapters 7 and 8, but now in terms of rotation. Okay, so rotational energy. Specifically, for now, rotation about a fixed axis. Okay, let's begin with a point particle rotating about an axis. Once again, the axis is fixed. Let's come up with the rotational equivalent, if you will, of kinetic energy. Okay, so right here is a fixed axis, like so. Here's a point particle of mass m. Right here is a moment arm with magnitude r. Once again, the center of the diagram here is the axis of rotation. Let's say that the object is rotating counterclockwise on the diagram. So at this moment, its velocity vector v is in this direction like so, tangential to the circle. Now, kinetic energy, as it always is just 1/2 mv squared. But now what I want to do is I want to rewrite this expression in terms of rotational quantities. The way that we do so is replace the linear speed v with r omega, where omega is the angular speed. So let's just go ahead and plug that in and see what happens. Okay, so kinetic energy K is 1/2 m and then times v squared. So 1/2 m r squared omega squared. And notice that the mr squared that I pick up here is the rotational inertia I of a point particle. So then therefore in rotational form, kinetic energy is 1/2 I omega squared. Like so. Okay, now that's for a single point particle. What about a distribution of matter, like a disk or something like that, rotating about the axis? Well, we'll picture this once again by using this little stick demonstration. So imagine that I have 2 point particles here that are making up a portion of a rigid object, and that rigid object is rotating like so in some manner. Each individual particle has the same value of angular speed omega at any instant in time, because if it's a rigid object, then each of these point particles is rotating through the same angle per time. So essentially what I'm going to do is just do a brief repeat of this description here, but let's do so in terms of the ith particle making up the distribution of matter. Let's redraw the diagram. Okay, so here's how I'll picture a distribution of matter. Once again, axis of rotation. Okay, here are 2 particles then within that distribution. Okay, and then right here is a little m sub I, and then let's just draw the other particle off to the side. Okay, and that little m sub I here has a moment arm like so with respect to the axis of rotation, the magnitude of which is r sub I. And then once again, let's say it's rotating here counterclockwise on the diagram. So at this moment, it has a velocity vector v sub I in this direction. So then therefore, the kinetic energy of the ith particle is just 1/2 mv squared. So k sub I is 1/2 m sub I v sub I squared. And then let's once again replace the v with r omega. But all of the particles have the same omega. Each particle turns through the same angle per time because it's a rigid object. So I'm going to replace the v sub I with r sub I times omega, like so. So let's go ahead and plug that in. Then when you do, you end up with this. And then what we'll do to get the total kinetic energy of the system is we'll sum over the I particles. So the total kinetic energy is the sum over the I particles. So that's the following summation. Let me write it like this. Like so, because what I do right here is the rotational inertia I of the system. So that therefore the total kinetic energy is 1/2 I omega squared, where the I here, the rotational inertia, is once again about this axis right here on the diagram. All right, so that's briefly how we describe kinetic energy in a rotational sense. It's just 1/2 I omega squared. Next, we describe work, and we also describe the work energy theorem. The work energy theorem involves a net work calculation. Okay, so let's go through that next. so work and the work energy theorem. Okay, let's just begin with a point particle once again. Okay, so here's a fixed axis. Here's my particle of mass m undergoing a rotation. And then we also have here a moment arm, like so, the magnitude of which is r. And then let's say that we apply a force, like so, F. Okay, well, go ahead and make this a vector, like so. Okay, now that force F in a little while will be in terms of the net force when we eventually get to the work energy theorem. But for now, let's just describe work and nothing more than that. Now recall, of course, from chapters 7 and 8 that work is the following integral. Here's how we saw it back in chapters 7 and 8, this line integral here where dr is the infinitesimally small displacement. Sometimes here in the context of the rotation, you're going to see a notation change. And the reason for that is because the dr is a little bit confusing in this integral. It implies that it has something to do with the moment arm. No, that's not the case. In this case, the dr is a little arc length on this circle. So then therefore, for that reason, sometimes you'll see the following notation to describe work in a rotational context. Instead of writing it as a dr, sometimes we write it as a ds for that reason. Like so, where ds is an infinitesimally small displacement describing an arc length on the circle. So on this diagram, where is this ds? Well, the ds is basically right here, tangential to the circle, like so. So then therefore, what we're calculating is this dot product. It's this dot product between f and ds. Well, once again, of course, we want to write this in terms of rotational quantities. In order to do so, we basically have to turn this into a torque expression. So here's then how we go about doing so. First thing I'm going to form is an angle between the moment arm r and the force vector F. We'll do so here off to the side. That looks like this. Okay, and then right here is our angle theta. Okay, now on this diagram, when we calculate this dot product, do we need this angle? No. The angle theta is the angle between the marker and the force vector. What we need is the angle between F and ds. That's this angle here. This angle here is the complement of the angle theta. It's 90 minus theta. So this green angle here is 90 minus theta. Let's go ahead and take the dot product now where we take into account the cosine of that angle. Okay, so work then therefore is equal to integral f dot ds. Okay, so this is going to be f ds cosine of 90 minus theta. So let's go ahead and use the subtraction identity for cosine. Okay, so work is going to be integral of f ds. Okay, and then in brackets here, we'll have cosine of the first angle, cosine of the second. Then there's a sign switch, if you remember, for the subtraction identity for cosine. So plus the sine of the first angle times the sine of the second, like so. Okay, in the first term, cosine of 90 degrees is equal to 0, and the second term, sine of 90 degrees is equal to 1. And then therefore, this simplifies to become the following. Okay, so work is going to equal integral of first f and then sine theta and then times ds. Like so. Okay, and now let's get rid of the ds. Let's write that in terms of an angle. ds is an infinitesimally small arc length. Recall that angle is equal to arc length over radius. So arc length equals radius times angle. Let's go ahead and write that into here. Like so. And now if I write it as I've done, this right here is describing the magnitude of the torque vector. Recall, of course, that torque is equal to r cross f, where the magnitude of the torque vector is rf sine theta. That's right here. So then therefore, we end up with the the following. So this is the general integral to describe the work done in a rotational sense. For now, we're just talking about a single point particle. In just a few moments, we'll extend this to a distribution of matter, and we'll get to it in terms of the work energy theorem. But for now, the rotational equivalent of this basic integral here is this expression here. If you're talking about constant torques, for a constant torque, then this integral is basically just torque times angle. Like so. Okay, and now watch the units here. Recall that the units of torque are meters multiplied by newtons, and then we're multiplying by an angle in terms of radians. So what we're doing here is we're like torquing an object through a distance, if you will. We're torquing an object through an angle. Therefore, the units are Newton meters, which are joules. So, okay, now briefly, before I get to the work energy theorem here, briefly, let's go ahead and divide this then by time to get a power description. So recall power is basically work over time. We saw this once again back in our unit on work and energy in chapters 7 and 8. Okay, so let me get rid of this. Okay, so power. First of all, there's the average quantity. If you recall, the average quantity was work over time. So then therefore it's basically this integral, or excuse me, this expression right here divided by time. So it's measured in terms of watts, joules per second. Okay, and then the instantaneous quantity is basically take a limit as the time approaches 0. Okay, the instantaneous power, we'll go ahead and write it like this. That's equal to the following. Like so. Notice that this expression right here is angular speed. Tau omega. So this quantity right here is the rotational equivalent of how we saw instantaneous power back in chapter 8. Back in chapter 8, we saw instantaneous power as the dot product between the force vector and the velocity vector. This is the rotational equivalent, torque multiplied by angular speed, okay? All right, now let's get to the work energy theorem. Okay, work energy theorem, and we'll describe this now in the context of a distribution of matter. So we'll have an ith particle, and then we'll add up over the I particles again. So let's draw the following. Okay, so right here is our little m sub I, over here is another m. Okay, here is r sub I. Like so. Right here is the net force applied to the ith particle, like so. Right here is the infinitesimally small displacement, ds sub I, like so. Okay, and then off to the side over here, here's r sub I, here's net force sub I. Right here is angle theta. Like so. Okay, so let's go ahead and calculate the net work that's basically done on the ith particle. So net work sub I, that's equal to integral f net sub I dot ds sub I, like so. Okay, here's a quick run through of the derivation that I just did a few moments ago. So this is going to be integral f net sub I ds sub I cosine of 90 minus theta again. Eating it up like so. Okay, so the 90 minus theta angle is this green angle again right here. Okay, run through the trig identity. That basically ends up being a sine of theta. so. Okay, replace the ds sub I with r sub I d theta. Everybody turns through the same amount of angle per time for a rigid object. So the net work of the ith particle is integral f net sub I times r sub I times sine of theta times d theta, like so. Okay, and then this right here is the net torque exerted upon the ith particle. Okay, so net work on the ith particle equals integral of net torque on the ith particle d theta. And now we add it all together. So the total work done is the sum over the ith particles. This then gives you the integral of the net torque exerted upon the distribution of matter over the angle theta. Okay, so basically all that I've done here up until this point is what I did earlier for a point particle, but just in terms of the I notation, and then I just added it all together. Okay, what do I do at this point to show the work energy theorem? Well, recall what net torque is equal to from the rotational analog of Newton's second law. It's I times alpha, where I is the rotational inertia of the distribution of matter, and all points within the distribution of matter undergo the same angular acceleration for a rigid object. Okay, so I have to integrate this quantity. In order to do so, let's replace angular acceleration alpha with d omega dt. That is like so. Like this. And then let's go ahead and reverse these two these two quantities right here, that is, like so. There we go, like that. And then this right here, angle over time, is angular speed omega. And now the variable that we are integrating over is the angular speed. So we integrate from an omega naught to an omega. Okay, and then we end up with the following. Okay, so find the antiderivative of this. It's 1/2 I omega squared, integrated between the following angular speeds, plug that in. And you end up with this quantity here, which is the change in the rotational kinetic energy. Like so. That's the work energy theorem in its rotational form for rotation about a fixed axis. Okay, let's go ahead and just take a look at a couple of simple examples in order to illustrate. All right, so let me do some erasing here. Okay, let's take a look at our first problem. So we've got a uniform stick of length 1 meter. So L equals 1 meter. Okay, its mass is 1/2 kilogram. Okay, it's rotating on an axis passing through the center of mass. So let's draw a basic problem here. So here's our stick. Here's the center of mass. Here's the axis of rotation. We'll say it's rotating like that. Okay, and it's initially rotating at a rate of 40 revolutions per minute. Recall that that's the frequency. So F naught is equal to 40 revolutions per minute. Let's go ahead and convert this into hertz. So we'll multiply by 1 minute per 60 seconds, like so, and then 40 divided by 60. I can't do this stuff in my head anymore. That's 2/3, it's 0.67 hertz. However, that's not the initial angular speed, that's the initial frequency. So the initial angular speed omega naught is 2 pi times that. So times 2 times pi, there we go. And that comes out to be about 4.19 or so radians per second. Okay, and then because of a frictional torque that occurs right here at the axis, The stick ends up at rest after 30 seconds. So the time t is 30 seconds, and the final angular speed is equal to 0. We're going to calculate a bunch of things here. Let me move the file. Okay, so first of all, in part A of the problem, it says calculate the angular acceleration. We'll just do a little bit of rotational kinematics to do so. So in part A, we'll use omega equals omega naught plus alpha t. The object comes to rest, so this is 0. And now let's just solve for alpha. So alpha ends up being the following, like so. And incidentally, the negative sign here means that the angular acceleration vector will point downwards on my diagram, because if I have the stick rotating like this initially, then omega naught points upwards like that. That's the positive direction. All right, so downwards is negative. All right, so let's see, omega naught and then divided by 30 seconds. And that comes out to be about negative 0.14 or so radians per second squared. Okay, now in part B, let's go ahead and find the frictional torque. The torque vector is going to point downwards as well. In order to calculate the torque, we'll just go I times alpha. Okay, so the torque is going to be I times alpha. All right, the I here is 1/12 ml squared for the stick being rotated in this manner about an axis passing through its center of mass, its geometric center. All right, so I still have alpha here in my calculator, and then I'm going to multiply by 1/12 times the mass of a half a kilogram, and then times 1 squared for the length squared. This comes out to be negative 0.0058 about. And this is torque, so this would be in terms of meter newtons, like so. Okay, now the energy lost as heat. In order to calculate the energy lost as heat, let's just set up the work energy theorem. So net work equals change in kinetic energy. Okay, take a look at the right-hand side of the expression. The final kinetic energy is 0, and the initial is 1/2 I omega naught squared. So then therefore, this negative number that we calculate here is all of the energy lost as heat, because the final kinetic energy is 0. So let's just go ahead and determine this number, and that's perfectly fine. All right, so negative 1/2, and it'll be negative because we're talking about energy lost as heat here. And then multiply by I, so by 12 times 0.5 times 1 squared, and then times omega naught squared. So times 4.19 squared, and this ends up being about negative 0.37 about. Our answer here in terms of joules. Okay, and then part D, the number of rotations made. There's a couple of different ways in which we can do part D of the problem. We could use rotational kinematics if we wanted to, but I'm going to use the work energy theorem here for part D to illustrate. Okay, now the net work done, this is going to equal then the negative of the net torque multiplied by the change in angle. There's a negative sign here, and the reason for that, actually the negative sign is already taken into account, in our calculation right here. This then equals the change in kinetic energy. There we go, the negative signs will work out like so, which was negative 0.37 joules. Okay, so then therefore, to find the angle is going to be this quantity here, like so, and then we'll divide then by the net torque. So the net torque was this guy right here. There's the negative sign. Like so. Okay, we'll end up with something in terms of radians here. So sometimes you just got to be a little bit careful in the negative signs, as I'm doing here. All right, so divide by negative 0.0058. Okay, all the negative signs cancel out, and I end up here with a total angle of 63 radians. So then, therefore, the number of revolutions made can be found from that. So the number of revolutions is going to be 63 radians, and then we divide by 2 pi radians per revolution. Like so, radians cancels, and we end up with number of revolutions. So divide by 2 pi, and that works out to be about 10 revolutions, like so. Okay, and then lastly, it's asking us for the average rate at which heat is dissipated. This is an average power calculation. So let me do some erasing here. So part E of the problem, average power, we'll just do work over time. Recall that negative 0.37 joules of energy is lost as heat in this problem. So let's just go ahead and use that number directly, and then we'll divide it by the time here, which remember was 30 seconds. So we end up with a small amount of watts. So negative 0.37, and then divide that by 30 seconds, and that comes out to be negative 0.012, give or take. Watts, like so, as an average rate of heat loss. Okay, easy plug and chug type of problem, but we're just using the rotational quantities, nothing more than that. Okay, let's take a look at a conservation of energy problem next. Let me go ahead and move the file to do so. Okay, let me go ahead and do some erasing here. Okay, so a uniform stick of length 1 meter and mass 1 kilogram. It's initially at rest, it's held horizontally. A frictionless pivot passes through one end. The stick is released and it rotates vertically. Find the speed of the center of mass at the bottom of the swing. So here's what's being described. We have a uniform stick, and then right here at the end is a pivot. The pivot is frictionless, okay? Obviously I'm holding it with some friction, we'll ignore that. And then what we do is release it from rest and it swings like so. What we're asked to find is the speed of the center of mass at the bottom of the swing when the stick is like this, okay? All right, so because the pivot is frictionless, this then means that it's going to be a conservation of energy situation. So let's kind of draw it out like so. Okay, so right here is the pivot. Right here is the center of mass. The stick has a length m and a mass m associated with it. Okay, its mass m is 1 kilogram, and the length L, excuse me, that's equal to 1 meter. Okay, so then we drop the stick from rest. The initial speed V naught at the center of mass is equal to 0. And then here is then the end of the problem. So the center of mass basically does this on the diagram like so. And right here at the bottom of the swing, there's a speed of VCM that we're asked to find. Okay, so we'll just set up conservation of energy to make this calculation. But when it comes to the change in potential energy, we need the height change. What is the height change to focus on here? The height change is the height change of the center of mass. And the reason for that is because recall that the external force of gravity mathematically behaves as if it's only applied to the center of mass. So for that reason, then the height change here in question, h, that distance is given to us as L over 2, like so. Okay, so let's go ahead and fill in our terms here. Okay, first of all, change in kinetic energy. Our final kinetic energy is going to be 1/2 I omega squared minus then the initial kinetic energy of 0. Okay, and then change in potential energy. We'll say that this right here is height 0. So then therefore final potential energy minus initial looks like this. We'll replace the h with an L over 2 in just a moment. Okay, and then we've got these terms here. First of all, I is the rotational inertia. We're pivoting the stick in this manner right here, so then therefore I is 1/3 ml squared, like so. Okay, and then let's write the omega here in terms of the VCM. So V is equal to R omega. The R in this case is going to be half the length of the stick, like so. Some variations of this problem will ask you instead to find the speed of the bottom of the stick. This then means that you would have to write the V down here as R omega. You would have to write it as L times omega, the entire length of the stick. So just be a little bit careful about what they're asking for in individual examples such as this. Regardless, however, the height change h is in terms of the height change of the center of mass. That doesn't change if we're talking about trying to find the speed at the bottom of the stick. Okay, at any rate, however, let's go ahead and plug everything into the expression. I'm going to move the mgh here to the other side. So mg times h, which was L over 2, equals then 1/2 I omega squared. So 1/2 times I, and then times omega squared. So the omega is 2 VCM over L. I have to square that. So 4 VCM squared over L squared, like so, for the omega squared. Okay, a bunch of stuff here is going to cancel out. These 2's are going to cancel, and L squared cancels here and here. and an M cancels here and here. And does anything else cancel? Doesn't look like it. Okay, so let's go ahead and simplify. Over here on the left, we have GL. And then on the right, I've got 4/3, like so, times VCM squared. Like so. Cross multiply the 3/4 to the other side and take the square root. And you end up with the following expression, like so. Okay? Notice that this is analogous to the square root of 2GH, for example, that we saw earlier in conservation of energy problems with roller coasters and so on and so forth. But this is all, of course, taking rotation into account. All right, let's go ahead and calculate this out to finish the example. So square root of 0.75 times 9.8 times 1 meter for the length. This ends up being a speed of about 2.7 meters per second. Okay? All right, so that concludes this lecture on rotational energy about a fixed axis.